Hello everyone, welcome back to the course Digital Signal Processing. In the last class, we were discussing about the frequency domain sampling and the reconstruction of the discrete signal. So let us go back once again. So what we were discussing in the yesterday's class. So we considered a Fourier transformation, that is we have considered a non-periodic signal. For the non-periodic signal, we have applied a Fourier transformation. And we know that when I apply a Fourier transformation for the non-periodic signal, the Fourier transformed signal will become a periodic signal. And for this periodic signal, what we are trying to do is we are going to discretize the values over the fundamental period 2 pi with a n number of samples. So therefore, in place of e power j omega, in place of omega, that is angular frequency, I am going to discretize with the use of n number of samples. And if you want to collect a particular number of samples, so in order to do that, we are going to do the indexing term, that is a k. So the k will take a value from 0 to n minus 1. So therefore, you'll be getting x of k is equal to 2 pi k by n, where the right hand side of the expression will be n is equal to minus infinity to plus infinity x of n into e power minus j 2 pi k n by n. Since we know that the Fourier transformed signal, it is a periodic signal, so it is necessary for us to represent, or we can represent this in terms of infinite number of summations of sum of each summation consisting of n number of samples. So we have represented this sampled version of the x of omega over this, and then since the given each samples is a periodic signal, it is possible for us to represent the entire summation with two summations in this manner. And we have represented, or we have introduced one more important factor, that is nothing but a periodic signal xp of n, where xp of n is nothing but summation l is equal to minus infinity to plus infinity x of n minus l into n. And we can see that this xp of n, we have done a Fourier series analysis. Since it is a periodic signal, for the periodic signal we can represent this xp of n in terms of Fourier series, and where Fourier series, the coefficient c of k can be written as 1 by n summation n is equal to 0 to n minus 1 xp of n into e power j minus j 2 pi k by n. And if you correlate this expression number 4, expression number 6, and expression number say, we can say that ck is nothing but the Fourier transformed signal, that is a discrete version of your x of omega we will be come to know. So therefore, we can represent this ck is nothing but 1 by summation 1 by capital N, that is a fundamental period n, summation k taking the value 0 to n minus 1 x of 2 pi k by n, where k is holding the value 0 to n minus 1. So therefore, we can reconstruct, that is a periodic signal xp of n, by using this expression, that is nothing but 1 by n summation k is equal to 0 to n minus 1 x of 2 pi k divided by n to e power j 2 pi k n by n. And this is possible only when we need to find the relationship between the xp of n and x of n. If xp of n is perfectly reconstructed with x of n mean, then we can represent or we can make use of this as a reconstructed signal, or else it is not possible for us to have a perfect reconstruction of the original signal x of n. So therefore, we have seen in the last class three important phenomena where we can reconstruct this xp of n will be x of n. When the fundamental period what we have selected for the xp of n, if it is larger than the number of samples which were there in the original signal x of n mean, then we can have a perfect recovery that we can replace this xp of n into x of n. Whereas if the fundamental number of samples what we have considered for the xp of n, if it is less than the number of samples what we have in x of n mean, then the aliasing will take place. It is not possible for us to reconstruct the original signal. So therefore, your x of n in the reconstruction phase, it will be 0. So therefore, we will not get a perfect original signal what we have discretized through the use of the Fourier transformed value. So therefore, it is necessary to have a x of n should be equal to xp of n only when you need to take the non-periodic signal with a fundamental period which is greater than this value. So if I do that, then it is possible for us to have a reconstruction from the discretized version of the Fourier transform signal by using this expression, that is nothing but x of n is equal to 1 by n summation k is equal to 0 to n minus 1 x of n into 2 pi k n divided by n. So if I substitute this value, so you'll be getting, that is the one of the term what we are going to get, that is p is equal to summation 1 by n is equal to taking the value 0 to n minus 1 e power minus j omega n. So if I substitute that, so this is the expression what you are going to get. So if I plot this with respect to the number of samples, that is angular frequency over here, so this is the what you are going to set, that is signal what you are going to get from this signal. So in summary, so what we can get is the finite duration sequence x of n. For that, we can have a discrete Fourier transformation, which is given by the expression in this manner. That is nothing but x of omega is equal to summation n is equal to 0 to L minus 1 x of n into e power minus j omega n, where omega is taking the value, discrete value 2 pi k divided by n. So therefore, we can represent the discrete version of this x of omega by using the fundamental period 0 to n minus 1 by using this expression. That is nothing but summation n is equal to taking the value 0 to n minus 1 x of n into e power minus j 2 pi k n by n, where k is taking the value 0 to n minus 1. Similarly, we can recollect the sampled version of your x of k to get back to the original signal x of n by using an inverse DTFT formula. So what is the inverse DTFT formula is extracting the x of signal from the discretized version of the discrete Fourier transformation. It is nothing but an inverse DFT formula. So by using the inverse DFT formula, so this is the inverse DFT formula what we are going to use in order to recover the original signal x of n. So that is nothing but 1 by n summation n is taking the value 0 to n minus 1 x of k into e power j 2 pi k n by n, where n is holding the value 0 to n minus 1. So these are the two important equations what we are going to study. If you remember these two equations, then several problems we can able to solve. Therefore, I request all the students kindly make a note of these two equations very well, and you need to remember at any instant of time. So most of the problems what we are going to solve it in the digital signal processing, which holds on only these two expressions. Okay, so one we call it as a discrete Fourier transformation, and one more we call it as a inverse discrete Fourier transformation. And how exactly we are trying to do this? A non-periodic signal first we are considering, and we are taking a finite set of values. For that finite set of values, the non-periodic signals we are representing in the form of periodic signal, and for this periodic signal we are applying a DFT value. That is nothing but you can see here a non-periodic signal we have taken, and we have selected some portion of this non-periodic signal, and this non-periodic signal, it has been represented in terms of periodic signal by using an imaginary periodic n number of samples, and these n number of samples, it has to be taken larger so that it is possible for us to have a reconstruction from this to this signal only when there is no aliasing will takes place. That is the number of samples what you are going to consider or what you are going to select for representation of this, then it is possible for us to recover the original signal from the sampled version. So that is where we are going to apply a DFT. So DFT basically it is nothing but a discrete Fourier version of your Fourier transformation. We call it as a discrete Fourier transformation. Now let us try to look on this. So what are the important formulas we need to remember? So the first one is DFT. So the DFT of the given equations will be calculated by using this expression, that is nothing but x of k is equal to summation n is equal to 0 to n minus 1 x of n e power minus j 2 pi kn by n, where k is taking the value 0 to n minus 1. And we can represent this e power minus j 2 pi kn by using one more important formula or one more important term, that we call it as a twiddle factor. So this twiddle factor also we are going to represent. This twiddle factor we will be using in order to represent the DFT and IDFT expression, where twiddle factor is given by W of n or omega of n, we will be calling it as. So omega n is nothing but a e power minus j 2 pi by n. So it is nothing but cos 2 pi by n minus j sin 2 pi by n. If I substitute that expression in this given expression, so you'll be getting the discrete Fourier transformation of the given signal x of n will be represented as summation n is equal to 0 to n minus 1 x of n into e power omega n to the power of kn, where k is taking the value 0 to n minus 1. So when you want to solve this DFT equation, so what you are supposed to do is basically you need to expand this summation. So what are the summations values it is taking? It is taking n, the value is taking 0 to n minus 1. So when n is equal to 0, what you will be getting? X of 0 omega n to the power of k into 0. So it will be 0, and x of 1 omega n to the power of k into 1 plus x of 2 into omega n to the power of 2k plus so on up to what is the last sample you will be having. So you will be having a n minus 1. So therefore you will be having x of n minus 1 omega k to the power of n minus 1 will be having. Similarly, the inverse DFT formula we are going to use, x of n is nothing but 1 by n summation k is taking the value 0 to n minus 1, x of k e power plus j is there, whereas here minus j is there. So I request all the students kindly make a note of these two, because so most of the students will be making mistake. For the DFT you will be writing plus, whereas for the IDFT you will be writing a minus symbol. So that is not the actual case. For the DFT, it is a minus signal we need to use, and for the IDFT, you need to use a positive value you need to use it. So for this, if I represent this in terms of twiddle factors, you'll be getting 1 by capital N is equal to summation k is equal to 0 to n minus 1 x of k into omega n to the power of minus kn for n is taking the value 0 to n minus 1. Okay, so in the next class, we are going to see some of the problems how we can able to solve by using these DFT formulas. Thank you.